Okay, so I'm recording now. Okay, I'm recording now. So, yeah. So I will begin with chapter 4 actually. Yeah, chapter 4. Chapter 4 is about magnetism. Yeah, magnetism. Magnetism. Okay, so I will straight away go to here. Okay, I believe you during your SPM you learned before about this solenoid. This is the solenoid. Okay, so solenoid. When you connect the solenoid with current, okay, when there is current flow, yeah, current got current flow in the solenoid, it will generate magnetic field. Yeah. So provided this solenoid, you must have current flowing through the solenoid. When you have current flowing through this solenoid is something like a copper coil, copper coil, copper coil. So when you have current flowing through the copper coil, so it will generate magnetic field. It become like a magnet. Do you learn about before about this solenoid? We call this what we call this is about electromagnet. Do you heard before about this electromagnet class? Give me a thumbs up if you heard before. SPM you learned before, right? When this solenoid you have current flowing through, then it generate magnetic field. Good, yeah, you learned before this one. Okay, and this is what we call right hand grip rule. Yeah, right hand grip rule. We put it as right hand grip rule. Okay, it is actually to determine the direction lah. It's about the direction, yeah, of what, of the of the magnet, direction of the magnet, and also direction of the current. Okay, this is a right hand grip rule. So for example, if you have current passing through this solenoid, then we use this, then it generate magnetic field. Yeah, got north pole and south pole, just like the bar magnet. Bar magnet also, the magnetic field come out from the north. Yeah, this is the magnetic field. We put the symbol B. Yeah, the B is called the magnetic field. Magnetic field. Okay, come out and then enter the negative. Correct or not, class? Magnetic field come out from north, enter the south. Okay, so this solenoid also become like the bar magnet, got the north pole and south pole. Now, how to determine the direction of the magnet? If you have current flowing through, we use right hand grip rule. Understand? So right hand grip, take out your right hand, class. I want you to take out your right hand. So the thumb shows the north pole. Yeah, the thumb shows the north pole. The finger shows the direction of the current. Okay, maybe I show you through camera. Yeah. So want to show you through camera, maybe. Yeah. Okay, I think I show you through camera. So hopefully you can see me. I think wait hold on a second. Okay, I think just make it bigger. Okay, I just want to show you how turn on my camera. Yeah, just turn on my camera. Oops, why so small? How to make it? Sorry. How to make it bigger? Class? How to make it bigger? I forget already. Okay. Can you see, class? Can you see me? Never mind. Can you see? Yeah. So I don't know how to make this bigger. Yeah. So yeah, I don't know how to make it bigger. So okay, right hand grip rule means like this. Yeah. Right hand grip. So this is my right hand. So this is the thumb. Okay, and this is the forefinger. The thumb is the north pole. The thumb is the north pole. The forefinger is the magnetic field. The forefinger is the magnetic field. Ito what I'm saying, sorry. The thumb is the north pole. Yeah, the magnetic field is the thumb, north pole, and the forefinger is the current. Okay, the forefinger is the current in the wire. So for example, like I have an electromagnet here. Okay, so so I put my hand around. Okay, so let's say my current is going this way. So this is my see my thumb. So this end will be north pole. Okay, so the opposite end will be south pole. Okay, this is the north pole and this is the south pole. If my current is in this direction, then this end will be north pole and this end will be south pole. Understand? This end will be north and this end will be south. Okay, understand, class? All right. Okay. So all right. Let me. Okay. So okay. Right. Right. So okay. So this is the right hand grip lah. Okay. So as you can see, just now I put my forefinger. The forefinger is the direction of current. Okay. So my forefinger wrapping around, the electromagnet. So my forefinger shows the direction of the current. Yeah. Like this. Yeah. Travel in this direction. So my thumb shows the north pole. So my north pole is at this right hand side. This is north pole. So this side will be south pole. Okay. So right hand grip rule is to show the direction of the magnetic field produced by the current. Okay. All right. So let's move on to the next part. Okay. This is chapter 5 already. Okay. You need to know something about magnetic flux. So what is actually magnetic flux? Magnetic flux. Okay. Magnetic flux is the let me write it down. Okay, magnetic flux is the number of magnetic field lines. Magnetic field lines passing through a certain area. Magnetic flux is the number of magnetic field lines that passing through a given area. Like you see this one. This area. I have a area over here. So the blue line is the magnetic field line. The blue line is the magnetic field line. Okay, as you can see, this magnetic field maybe is produced by maybe produced by the magnet. Here you have a north pole and here you have a south pole. Yeah, you put this is a bar magnet lah. Yeah, just a bar magnet. Okay, so bar magnet north. So magnetic field. Yeah, this is, you see, this is the direction of the magnetic field. B is the symbol of magnetic field. So magnetic field always come out from north and go to the south. Okay. And what is magnetic flux? Okay, what is magnetic flux? The magnetic flux symbol is this one. We call phi. We call it phi. Okay. What is magnetic flux? Magnetic flux is, let's say you have an area like here. Yeah, this area. Just an area lah. Yeah, satu keluasan kawasan. Okay, so magnetic flux is the magnetic field lines that passing through this area. Passing through this given area. So like you see here, how many magnetic flux are there? One, you can count the number of magnetic field lines passing through the area. 1, 2, 3, 4, 5, 6. Maybe this one 7, 8. You see, got 8 lines. This one is not passing through the area, so this is not magnetic flux. So these are magnetic flux that pass through the area. So let me maybe redraw something like this. Yeah. So let's say you have a magnetic field line. You know, magnetic field line. Magnetic field line. Okay. Okay. Let's say I have a copper coil. You know, copper coil. Over here. Yeah. This is a coil. Yeah, a coil with an area. You know, it has certain area. Area. Okay. It has an area. Okay. So this black line is we call the magnetic field line. Magnetic field lines. These magnetic field lines, why you have magnetic field here? Because maybe here you have a magnet north and you have south. Understand? You have a bar magnet here. You have a bar magnet. Okay. So you have magnetic field lines, and the symbol for magnetic field is B. Understand? So you have a coil here. Maybe this coil maybe is a copper coil. Okay, a copper coil. A copper coil. All right. So so the magnetic field lines that passing through this area, this yellow area, is called what? Class, is called what? Tell me. What's the name? Magnetic? Magnetic? So shy. It's called magnetic flux. Understand? The magnetic field line passing through this area is called magnetic flux. So how many magnetic flux you can find here? So here you have how many magnetic flux? So so for here you can see the 1, 2, 3, 4. Understand? So these blue lines are called magnetic flux. Understand? Okay? Okay, everyone? Okay. Yeah, I didn't see your hand just now. Yeah. Oh, I'm showing my. I should off my camera. Yeah, I should off my camera. So it's I should off my camera. Turn off. Okay, I turn off already. I should unpin. You know, unpin it. Okay. Just now become smaller. My yeah. All right. Okay, class. So now you know what is magnetic flux. Magnetic flux is the magnetic field lines passing through a certain area. Okay. So magnetic flux is the number of magnetic field lines that passing through a certain area. So this is the formula lah. Phi equal to BA cos theta. Okay. Another thing I want to say, class. Another thing I want to say is this bar magnet. Okay, bar magnet, we know it has north pole. Yeah, it has a north and south pole, right, class? So last time you learned about electrostatic. Okay, you learn about electrostatic. Electrostatic. Yeah, electrostatic. This is for charge lah. Yeah, last time is charge. Charge. Yeah, so charge is different from magnetic field line. Yeah, charge is different from magnetic field line. Charge is you know, you have like positive. You have what? Positive. You have this is what we call electric field lines. Electric field lines. Okay, but for magnet, magnet. Yeah, this is the what we call magnet, bar magnet. Okay, it has what? Last time electric field we use the symbol E. Now, if magnet we use the symbol B. Magnet we use the symbol B. So this is the positive. Okay, so like that. Understand? And then here enter. Correct not, class? So this is the magnetic field. Yeah, we call it yeah, electric. You have electric field lines. So magnetic field also have magnetic field lines. Okay. This is magnet. This is charge. So charge is electric field. Magnet is magnetic field. You can, just now you learn about solenoid also. Yeah, just now you learn about solenoid also. Solenoid also can become like a bar magnet. Also can produce this magnetic field. You have north and south. So this one not necessarily must be a magnet. It can be a solenoid also. Yeah, it can be a solenoid. So when solenoid also has produced magnetic field. Okay, why I want to tell you this, class? Because last time when we learned charge, nearer to the charge, like for example this position, yeah, here it has strong electric field, isn't it, class? Strong electric field. But if very far away, it has weak electric field. Correct not, class? Same thing goes to magnet. Nearer to the magnet, it has strong magnetic field. But further away, for example, like over here, it has weak magnetic field. Yeah, nearer to the magnet, strong magnetic field. Okay, so you just look at the distance between the lines. If the lines are closer to each other, means it's strong. If the lines are further apart, they are weak. Yeah, just like the electric field. Understand? The magnetic field is just like electric field. So if closer to each other means strong magnetic field, weak, further apart is weak magnetic field. Okay, good. Finish about that. So you learn about these magnetic field lines. You also learn what is magnetic flux. Magnetic flux means flux through a certain area. Okay, like this. You see this. You have how many magnetic field lines? 1, 2, 3, 4, 5, 6. So you have 6 lines here. Only 4 out of 6 lines. Only 4 lines. Only 4 magnetic field lines out of 6 lines. Only the 4 lines are called magnetic flux. Only the blue lines is magnetic flux. The black lines not magnetic flux. Yeah, the black lines is not magnetic flux because it doesn't pass through the area. Sebab dia tak lalu area itu. So the black line not magnetic flux, but the blue lines are the magnetic flux. Understand, class? So if you look at the equation, this magnetic flux, you can increase the magnetic flux through several factors. Either you increase the magnetic field strength, or you increase the area, or the orientation of the theta is the angle between the area and magnetic field. But this theta I don't teach now. I will teach later. Okay, I just want to focus about this magnetic field and area. Okay, so it changes the magnetic flux. So you see, class. For example, class, like this magnet. If I put my coil over, let's say, over this position, if I put my area, my coil with area A, this area lah, yeah, it has certain area over here. Coil, a copper coil, yeah. So compared to I put the coil over this position. Yeah, I put the coil at these 2 different positions. Which one has more magnetic flux? Which one has more magnetic flux? Of course, the The first one, isn't it, class? The first one or second one, class? The coil 1 or coil 2? Which one? Coil 1 or coil 2? I cannot see your comment or anything unless you open your mic and tell me, because I only have one screen. I cannot look at the Google chat meet, so you open your mic and tell me and answer me, pity me, I'm the only one who talking now, okay. So okay, so only the coil 1, so I can say based on this formula, flux equal to magnetic field BA cos theta. I can say based on this formula, magnetic flux equal to BA cos theta. So I can say flux 1 is more than flux 2. Because why? The magnetic field for 1 is bigger than magnetic field for 2. Correct or not, class? Bigger, because when the coil is nearer to the magnet, it has strong magnetic field. Like B1, it has strong magnetic field. So it has more magnetic flux. You have 5 lines passing through this area. For coil 2, only have 3 lines. So for coil 2, is further away from magnet, so it has weak magnetic field, so it has less magnetic flux. Understand, class? Understand? I want to see your thumbs up. Give me support. At least you don't open your voice. Also you give me a thumbs support lah. Emotional support. Okay. If not, sometimes teacher will break up. Will stress and break up. Okay, never mind. So that is one way to increase the magnetic flux. Either you use a strong magnetic field or weak magnetic field. Magnetic flux. So if I increase the area, of course, I also increase the magnetic flux. Like for example, if I increase the area, for example, I have another coil. Maybe I put a coil 3 over here. Bigger area, coil 3. See, coil 3. So coil 3 has bigger area, isn't it? Bigger area, so more magnetic flux. Now instead of just 3 lines, I have 5 lines. Correct or not, class? Increase the area, increase the magnetic flux. Correct. Good. Like that lah. Okay, that's all. And then now I want to move on to the next part. Hopefully you understand. Either you use a strong magnetic field or bigger area. Then you have more flux. Magnetic flux is the number of magnetic field lines passing through a certain area. That's it. Okay, so the next part is just now is about only magnetic flux, a small phi. Now is called magnetic flux linkage. What's the difference, class? Let me write above here. Just now you learned about magnetic flux. Magnetic flux symbol is a small, small letter. This is a small phi. Small letter. It's a Greek word lah. Actually, it's a Greek word. This one also a Greek word. This is also a Greek word. Small letter. Now magnetic flux linkage. Got the word linkage here, class. Linkage. What is linkage, class? This one linkage. This is capital letter, class. This is capital letter. This is also phi. But the way we write it is capital letter. That means it's like this. If magnetic flux only is small phi. If magnetic flux linkage, we write as capital phi. Capital phi. This is the capital letter. Okay, class? What is magnetic flux linkage? You have an extra word linkage over here. What is it? Last time, magnetic flux is just one coil. Yeah, magnetic flux is just for one coil. Like you see, only one turn. Magnetic flux linkage is many turns. Many turns through n turns. Okay, so that's the difference. Magnetic flux, the small letter one. Just write off this one first. This one is for one, or we can write n equal to 1. This is only one turn. Yeah, one turn. If magnetic flux linkage is, you have n turns. You have many turns. Many turns. Many turns is like many area. Many, instead of just one area, now you have many areas. Isn't it, class? Yeah, now you have many areas. For example, like the example just now. Yeah, now last time I used only one turn. One turn. So the area is considered only one area. Now if I use multiple area, if instead of just one area, I use one. You see, if I use one area, one turn, one area, two turn, two area, three turn, three area, four turn, four area, five turn, five area. So let's say I have 5 turns. I have how many area? 5 area, isn't it, class? I have 5 area, means I have 5 area. I have 5 area. 5 area. I can put this as 4 lah, number 4, coil 4. 5 area. Last time we learned more area, more flux. Isn't it? More area, more flux. Last time I used one area, I only have one area of flux. Now if I have 5 area, 5 turns, 5 copper coil, I have 5 area of flux. Multiply 5 lah, isn't it, class? The flux multiply 5, isn't it? So it's like become last time is only one flux. Now it become 5 flux because I have 5 area. Multiply 5 lah. Correct or not, class? Give me a thumbs up if you understand. Give me a thumbs up if you understand. Okay, good. Thank you for your thumbs up. So heartwarming, yeah. When I hold on a second. When I teach, I is coughing, yeah. Okay, class. Okay, humans are imperfect. Always have diseases, yeah. Okay, that's why you see this is called magnetic flux. When you have many turns, multiple turns, n turns, many areas, we don't call it magnetic flux. We call it magnetic flux linkage. All the turns link together, linkage. So is correct lah, this formula. So magnetic flux linkage is n phi. Last time phi flux is only for one area. Yeah. This one is only for you see here, the flux is only for one turn. So if you have n turns, you multiply n. Correct not, class? You multiply n. So magnetic flux linkage is n phi because you have 5 area, then you multiply 5. So the formula you can also write as you can write flux is BA cos theta, so it's n BA cos theta. Okay, later future we will learn more deeper about this. Yeah. Okay. So in short, what I can say, class, how do you change the magnetic flux linkage? How do you change the magnetic flux linkage? It's either you increase the area, use a strong magnetic field, or you have multiple turns. Then you can increase the magnetic flux linkage. Understand? This one you see magnetic field line go below. Meaning that Here it has a north pole, yeah, and here has a south pole. Yeah. Magnet lah, a bar magnet. Okay. You use more area, more magnetic field, more turns. Then you have more magnetic flux linkage through a copper coil. Understand? Okay, class. I don't want you to be how to say confused. Last time we learned about electromagnet. This one generate generate magnetic field, right? And this one is about magnetic flux. Magnetic flux. This magnetic field is not generated by the coil. This magnetic field is external magnetic field from the magnet, not from the coil. Yeah. So this one is different. This one is I don't want you to get confused. This one is you have current in solenoid, then the what we call solenoid generates, yeah, solenoid generates when you have current in solenoid. This solenoid generates its own magnetic field. This one is when you have current in solenoid, this solenoid generate magnetic field. This magnetic field comes from the solenoid. Understand? But just now we learned about magnetic flux. Okay. What is this? Okay. Just now we learned about magnetic flux linkage. This magnetic field is not from the coil. This magnetic field is external magnetic field. Yeah. This is external. This external magnetic field. External magnetic field from where? External magnetic field from bar magnet. This bar magnet also external lah. Yeah, mean outside. This magnetic field doesn't come from solenoid. This magnetic field comes from outside. So I'm just letting you know that a term called magnetic flux linkage. Yeah, magnetic flux linkage means that if I have put a coil over here with external magnetic field, okay, external magnetic field, the lines that passing through this coil is called magnetic flux linkage. Linkage means you have multiple turns. Understand? So this magnetic field is external, not internal, not from the coil, meaning that this coil now it doesn't have any current, no current at all. Now it has no current. Now this coil it has no current yet, no current. Yeah, no current. No current, and it receives external magnetic field. Last time we learned about solenoid. Solenoid, this one is you have current. You have current in the solenoid, then it produces its own. The solenoid produces its own magnetic field. Okay, that's the difference. You understand, class? Do you understand about this one?
Yes,
okay, I will help you keep track. You keep track. Okay, good. So that's the difference. Yeah. Okay, now, class, I want to go to the next one. This is the important part. Faraday's law and Lenz law. What I'm trying to do in today's lesson is about how an electric generator works. Electric generator. You know, dalam station tenaga hydro atau tenaga apa lagi? Tenaga angin kan? Station jana electric. How they produce electric? Even in your bicycle or in your car, they have this called dynamo. You know dynamo? How they generate electric? How they generate electricity? So that's why we are learning about all these magnetic flux linkage, and now this Faraday's law and Lenz law will explain how this electric generator works. Understand? So just now is the preliminary knowledge. So now is the the concept I'm going to teach you about how the electric generator works. Yeah. So class, Faraday's law is very important. Faraday's law implies that an induced EMF is produced when there is a change in magnetic flux in the coil. This is the key of electric generator. Electric generator. Yes, you can generate electric in a coil if you do this. If you do this, what should you do? Faraday say, how do you generate the electric? Yeah, electric generator. How do you generate an electric? How do you generate the EMF? Induce means what? Induce means generate lah. Understand? Induce means you generate. How do you generate the EMF? EMF means electric. How do you generate electric? How do you produce the induced EMF? How do you? When, this is the most important statement here, class. This is the most important statement here. When there is a change, in magnetic flux in the coil. This is the most important statement here. When there is a change in magnetic flux in the coil. How do you generate electric, class? When there is a change in magnetic flux in the coil. So why you learned about magnetic flux just now? What is magnetic flux? You need to go back to what is magnetic flux. Magnetic flux is the number of magnetic field lines passing through a certain area. Okay, certain area. So like you have like this one, you see, like you have this area. Okay. This 5 electric field line passing through this area is called magnetic flux. So how to Faraday say, how do you generate electric? You generate electric when you have a change in this magnetic flux in a coil. Just that simple. When you have a change in the magnetic flux in the coil. That means what? That means like this. If you move this coil, careful class, pay attention. If you move this coil 1 from position 1 to position 2, assuming that this coil here and this coil is the same coil, 1 and 2 is the same coil. If I move this coil from position 1 to position 2, or position 2 to position 1, is there any change in the magnetic flux? Is there any change in the magnetic flux? Yeah? Position 1 and position 2, do their flux the same? Is their flux the same? Different, isn't it? Position 1 has more flux. Position 2 has less flux. Because when you're further away from the magnet, it has weak magnetic field. So when weak magnetic field has less flux. When position 1 nearer to the magnetic field, nearer to the magnet, it has strong magnetic field, it has more flux. So how to generate electric in this coil from 1 to 2? So is if coil move from, okay, I think I should I tired of just writing like this. I should just type, I should just type. I should change the font, become bigger, because it's very, very, very small. Okay. So pay attention to this one. Faraday say when the coil moves from position 1 to 2, flux, what happened, class? Flux increase or decrease? Flux increase or decrease, class? Tell me, class. Never pity me. Flux increase or decrease when move from position 1 to position 2? Flux increase or decrease? When coil move from position 1 to position 2, the magnetic flux increase or decrease? Yeah? Increase or don't type there lah. You type there, very hard to increase. When move from position 1 to position 2, increase or decrease? Flux increase or decrease?
Decrease.
Decrease. Good. Flux decreases. Okay. And how about let's say good. Yeah, flux decrease, not increase. Okay. How about class? I put it like this. How about if I move, let's say I move the coil from position 2 to 1. If I move the coil from position 2 to 1, what happened to the flux, class? Come on, I need to hear your voice, your beautiful voice. Yeah. That's why.
Increase.
Yeah. The flux increase or decrease if I move the coil from position 2 to position 1. What happened to the what happened to the flux? Say again, please.
Flux increase.
Flux increase. That's good. Flux increases. Okay. So this action, when you do this, class, when you do this, this is the this is the action. This part is the action. When you do this, either you move from position 1 or 2, 1 to 2, or position 2 to 1. What happened to the flux? Is there any changes? Yes, there is a changes in flux. Understand? It's maybe decrease or increase. So we call this flux increase, decrease, or increase. These are called delta phi. Delta phi. Understand not? Changes of flux. Understand not, class? So the flux changes. Yeah, the flux changes. Yeah, maybe it decrease or increase. So what will happen according to Lenz law? Go back to Lenz law. What happened if you have delta phi? If you have changes in the flux, yeah, either going from 2 to 1 is increased flux. 1 to 2 means decrease in flux. Okay. So in either cases, you have changes of flux. Changes of flux. So what Faraday says about this? Faraday's law says an EMF is generated, dihasilkan, when there is a. Come on, you tell me when there is a. When there is what?
Change in magnetic flux.
When there is a change in magnetic flux in the coil, when there is a delta phi in the coil. So these changes can either say that either flux increase or decrease. Yeah, this is how you generate electric. You change the magnetic flux. Passing through the coil. Yeah? How do you change the flux? It's either you increase the flux or you decrease the flux. Yeah. So this is the formula, class. EMF is induced equal to negative d phi over dt. Okay? So this is the one. Yeah. So it's delta phi. That means it's you can delta, yeah, or you can write it as this way, delta phi or delta t. So means you have flux final minus flux initial. Delta phi means you have final minus initial. Final flux minus initial flux. Means because the flux either increase or decrease already. If of course if you have multiple turns, yeah, this one actually should be changes of flux lah. If you have multiple turns, there should be capital letter. Yeah. Okay. So when flux, like for example, like this one, flux increases. That means the final flux will be bigger than the initial flux. If flux decreases means the final flux is less than the initial flux. Less than the initial flux. So if you have changes of flux, like this case, you will produce an EMF. So like, go back to this example. If you move the coil from coil 1 to coil 2, what happened? If you move the coil from position 1 to position 2, what happened, class? Yeah, it will generate electric. So in the coil just now, it will generate electric. Got current flow in the coil already. Got induced current. Got current flow in the coil. Ada elektrik sudah. Kalau you bergerak dari 1 ke 2 akan ada elektrik. Kalau bergerak dari 2 ke 1 pun akan ada elektrik. Sebab ada perubahan flux. Okay, class. Now, this is about Faraday's. Yeah, this is about Faraday. Okay, this is about Faraday. Now, Lenz law is about the directions. Yeah, Lenz law is about the directions. Dia kata induced current always flow in a direction that opposes the change in magnetic flux that causes it. So now also 9:10. I don't think this one. Okay, I will actually I have example to like. Okay, I just show you an example like this one. Macam ni lah. The lastly, yeah, you look at this one. So if the solenoid, the solenoid you move towards the magnet. I see the solenoid you move towards the magnet. So there is a changes of magnetic flux through the coil. So you produce current in the coil. And what Lenz law nak terangkan ialah Lenz law is about saying the direction. Boleh begini, class. In short lah, I cannot say too much. Lenz law is about direction. Yeah, I just want to summarize. Yeah. For just few minutes. So Lenz law is about direction. Direction of induced EMF or induced current. So direction dia apa, kelas? Kalau you bergerakkan solenoid ke arah magnet, so kutub ini akan jadi north juga. When you move the solenoid towards the magnet, so there is a change of magnetic flux happen in the coil. There is delta phi happen inside the coil, so it will induce. That's why you have E induced equal to negative d phi over dt. Okay, when you have induced EMF, generate electric, so we know that E equal to IR, kan kita belajar V equal to IR. Bila ada voltage, ada current, betul tak? So E induced ini pun sama dengan I induced resistance. So bila ada perubahan flux, ya, bila ia gerakkan solenoid ke arah magnet, so ada perubahan flux dalam solenoid, so ada induced EMF. Bila ada induced EMF, ada current di dalam solenoid. So what is Lenz law? Lenz law says if the solenoid move towards the magnet, this part will become north pole also. Same pole. It try to oppose the motion. It try to oppose the changes. Bila nak mendekati, ini jadi same pole, become north pole. Okay. So here become north pole, and this part will become south pole. Now use your right hand grip rule. You can find the direction of induced current. Betul tak? So kalau sini north means the thumb shows the north. So the finger is macam direction of induced current lah. Understand? Kalau okay, I get got some example here, class. See, class. Macam example ini. Kalau magnet ini move towards here, kalau magnet move towards, this part become what pole, class? Tell me. It try to oppose the motion. Oppose the motion. What happened, class? Here become north pole also, same pole. Here become North Pole also. Because dia nak, kalau mendekati, saya cuba nak oppose. So here become North Pole. So we use this hand. Okay, we use this hand. So this is the north. So what happened is the magnetic field. So what is the direction of current? Look at the direction of current. So we have North Pole. That means here it has an induced magnetic field in this direction. Okay, north. Here is a south. Okay. So what is the direction of induced current? Tengok dia punya finger tu. Okay, saya tetap mau lukis ini dulu ya. Nanti lain kali baru saya ajar. So sini jadi north. So current dia bergerak macam mana? Current dia di sini. Induced current dia di sini. Ke bawah ya. Ke bawah sini induced current. Faham tak kelas? Okay, tengok ini. Kalau ini magnet sudah bergerak jauh, menjauhi. Lenz law says want to oppose the motion. So kalau menjauhi, sini akan jadi sini south yang bergerak menjauhi, so sini akan jadi north. Dia tak mau dia bergerak menjauhi. Sini akan jadi north, sini pula jadi south. Faham tak? So maksudnya pendek kata begini kelas. Saya begini ya. When habis sudah ya kelas, nak habis sudah sekejap lagi. So when approaching, okay, when approaching become same pole. Ini yang penting kelas, same pole. Okay. When moving away become same pole. Magnetic field become same pole to oppose motion. Okay, to oppose motion. When moving away, it become opposite pole to oppose motion also. You understand the yang penting ya. Oppose motion itu ialah tentang Lenz law. It's about Lenz law. Oppose the word. Okay. So when approaching, so bila approaching, dia akan call nak oppose the magnet lah. Dia nak oppose the magnet. So dia nak slow down kan magnet. Dia produce same pole. Same pole. Bila dia nak magnet nak moving away, dia nak slow down kan magnet juga. Dia nak tarik balik. Sini dulu dia datang, dia nak tolak. He want to tolak. Bila dia datang dia nak tolak. Bila magnet nak bergerak keluar, dia pula nak tarik. Dia selalu nak slow down kat magnet. So dia become opposite pole. Bila magnet moving away, become opposite pole to oppose the motion also. So boleh kata kalau ni south is coming, to oppose the motion, I become south here. Here become north. So when moving away, so when you coming, I try to tolak. Kalau you keluar, saya nak tarik pula. So macam mana tarik? Dia become opposite pole, become south north pula. Understand this class? About this right hand grid rule saya tak sempat nak ajar. Nanti eksperimen saya ajar lah. Okay. So understand class? Understand today's lesson? Understand? So sorry a rush because I teach a lot of things today. Okay, because I have to teach this before for experiment. Then you understand the experiment. So I will explain more about this through the experiment. Okay, class? Okay, sorry for extra time. Okay, thank you. Bye.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you,
Thank you, sir.
So
Thank you,
Dia
sir.
selalu oppose motion lah. Bila dia datang,
Thank
saya
you,
nak
sir.
tolak. Bila you keluar, saya nak tarik balik. Macam tu lah. Ya.
Thank you, sir.
Menghampiri, saya tolak. Bila you keluar, saya nak tarik. Begitulah. Itu saja. Okay, bye.